Okay, in this lecture 20, I'm going to describe 3 topics. One is to share with you some further characteristics associated with the observed elastic breakup during step shear, after step shear rather. And then I will move on to describe for you under what conditions we should expect the step strength to give you quiescent relaxation. Homogeneous yielding will not produce any motion. And lastly, I will use the example of a weakly entangled system to show you that in absence of any observable motion during the stress relaxation, how do we learn about elastic yielding?
All right, so last time we started to talk about what happens after large step strength. So today I want to dive a little deeper into this topic. So I'm going to try to review for you, particularly the relationship between the step strength and the startup shear. So chapter, if you like, we talked about startup shear in chapter 7. We talked about using PTV to observe what happens in startup shear in chapter 9. And those are all just startup. So you have a velocity all of a sudden build up, and you watch what happens stress-wise as well as the field-wise, the strength field-wise. So now we switch to this part 3, which is all about step strength. In other words, we're going to terminate. Instead of continuing forever, we're going to terminate our step strength, our startup shear. So this is what we have. We have this startup shear. If you monitor this whole startup process, the stress will build up, reach a maximum, and coming down. We talk about the scaling in chapter 7, and whether there will be shear bending or not after the overshoot in chapter 9. And it's interesting for you to appreciate the relationship between what we're doing in this chapter 12 on step shear, so-called, and startup, which is what we did here. And the relationship is rather straightforward if you don't dogmatically try to follow the textbook. Textbook says step shear need to be so fast that it's never considered as part of a startup. But it's always a startup because it takes finite time. It takes some finite time to build certain. I hope you guys are comfortable with this. How much strength is building? It's building x over h, which is delta T over V divided by H. That's how much strength you're building. Right? If I terminate here. So similarly, the response in stress is in purple, again, if we terminate here. That's what we have been doing. Terminate here, in other words, way before reaching the yield point, we terminate. So obviously your sample has been undergoing essentially elastic deformation, and then you terminate and watch and want to know what happened. And I motivated this a lot about wanting to know what happened, because it's supposed to be rather uninteresting, at least from the point of view of observing anything during relaxation. It's supposed to be quiescent. So when I say we dig a little deeper, I mean several things. So let's start with some details. This movie, you have seen it before, and I know this thing always doesn't recognize it. And this involves solution, and you can see the sample start to wake up before your shear scission occurs. In the this is for solutions, and I think you can really object to that somehow the solution is behaving rather funny because you only have 10% chance. There's so much loose space, so much space there, maybe something funny happened. So it is absolutely necessary to find out whether anything like this is true in melts. Absolutely necessary. So we struggled to do this. And luckily, turns out SBR with a high vinyl content. High vinyl content is such that you can use the supermarket super glue to glue your polymer to the steel plates. So basically, you're getting hold of a piece of SBR, of high molecular weight, that possesses a B that's rather large. So this will be, let's say, can be much larger than 1. So you will have plenty of wall slip if you don't superglue it. Or do something to fix it. So this is pure. I cannot imagine not having the superglue. What do you do? It will be massive amount of slip, and then you will not build enough deformation in the sample. In any case, Puyang, who is a faculty at Delft in Netherlands now, he had the patients and he glued the sample under the plates, and he showed that so melts, commercial rheometer, rotational rheometer can never handle melts, so we have to build a sliding plate homemade ourselves, and a linear displacement shear can handle 3 H's very easily because you don't have to involve too much strength. So he was able to show 10% deformation, that's just linear response. Even 70% deformation look like much like a linear response. You see, there's no kink. By the time he sheared just 2 H's to the right and hold it, he find nothing happens for a while, and then a kink occurred. That occurrence of kink occurs at around 10 seconds. And it turns out that's when the motion starts. In other words, it actually was largely motionless after shear scission for the first 10 seconds. Okay? So these are just his analysis of what happens. You see, basically this thing remains stationary. So I have to put my cursor here and wait for 10 seconds, and you will see how much motion there is. And these 2 graphs, now you see 10 seconds is this long. Now you see how much motion? Tremendous. It just falls apart after 10 seconds. So this analyzes at different times the speed with which it snaps back, because the middle broke. So whatever sheared, it want to snap back. And the other figure just tracks the particles that you initially identify particle vertically and find at a later time where the particle moved to. Okay? So again, he's trying to show in the first 15 seconds, particle didn't move anywhere. And after 45 seconds, these different particles along the gap moved away from the initial 0 line, initial position. So moved as much as, you see that's about a fraction of the gap. That's a lot. Remember, the gap is 0.7 millimeters. It moved about 0.2 millimeters on each side. Okay, right? So that's the phenomenology. So we confirm that melt also breaks apart. We're still far from figuring out why they break apart, and that's part of the theory yet to come. So if you move on, remember the science is always what, how, and why. So we know what question to ask, and we are going to just accumulate moving the next step about how. A little more of how. For example, if you have 3 different molecular weights, how this breakup occurs. I know by now you can probably connect between what I mean by breakup, meaning motion start to occur, to the kink. That's where the kink occurs. In other words, when the samples start to break up, the system is taking advantage of that, try to quickly release what's the build-up stress that's there. So the occurrence of the kink correspond to where the sample was about to break up. The onset of the kink is the onset of the breakup. Since we are on this page and with Rouse number on here, I may just indicate one crucial thing. The occurrence of the kink, experimentally we call it TK. The literature has accumulated a lot of knowledge about what TK is. And it has bothered people for quite a bit that this TK can be longer than Rouse time. Why it bothers you? Because the tube model had the feature that this kink can only occur around tau r, not later. It bothered people. People go, try to modify, try to see a few different things how they can change that, change the tube model. So in that sense, the tube model is not crisis-free. The right word, that's Thomas Kuhn's word. When there's a big change, is typically when you first encounter crisis. Crisis in our faith, I think, is the right word to say, actually. So it's not without crisis. I already mentioned that the damping function, you guys know very well now, that the tube model damping function only fits a subset of the data. So the other sets of the data should already cause you to panic. And this is another part that causes people to panic, because you can be very quantitative, that the TK is larger than tau. It's not what the tube model prescribes. So it bothers people. It did bother people. But we were not motivated by this particular feature. We were motivated, remember, by the over-damping function. The function was damping too much, right? So in any case, since we're on this page, I just want to indicate the fact this can be larger than tau r is another indication, gee, the tube model may not be the right, may not represent the right physics or disclose the right physics. So here, Puyang was just trying to show you that even though the TK can be larger than tau r, they still scale with tau r. So he used 3 different molecular weights. Therefore, the tau r spreads. And indeed, you find the kink spreads. Basically spreads about 10 times, about the order of magnitude nearly. But when he look at this kink in terms of the unit of Rouse time, it collapses. That's the inset curve. Similarly, if you look at the motion, it collapses. Okay, if he normalizes his time with tau r, then the motion occurred at the same place for the 3 samples. Yeah. But just the so-called the how part, because basically you accumulate, you know what question to ask, you now see a little more of how it happens, and then that eventually could give you the why, could lead you to think about why it could happen. So that's one feature. The other feature I should mention was something that I actually proposed and predicted, that I suggested that very counterintuitively, that if I use a lower rate to produce this step strand, that's the red, the rate was 0.7, versus a higher rate, which is 20 times higher, which is the green. I suggested that the red one, and you move 2 H's to the right for all the different 3 rates. The red one will break up first. That's the prediction. That's counterintuitive only in the conventional sense. Gee, the green one that involves more stress, shouldn't that break up first? Since you have more stress. But the argument I had was we already appreciate what this point means, the overshoot. So it turns out the lower rate one at 2 H's, you are closer to the overshoot than the higher rate one. The overshoot is over there. Okay, far away. So we perceive that the structure was already about to break up for the red one and still far from being able to break apart for the green one, for the higher rate. So you can argue then that the green one will have to struggle more for whatever physics that causes the breakup. Of course, conventionally you would think more forces should allow you to break up early, but you are so far away from the failure point, whereas the red one is about to fail anyway. So the shear scission actually induces. And indeed, this is true. This is all I'm trying to say, that the red one, the induction was 10 seconds, the green one was 25 seconds. Before any motion occurs. Sorry, I have a habit of assuming everything you know. So this plotted is vertically is plotted as the motion of the particle, and this axis is just time. So it turns out you have to wait 10 seconds before any motion is detectable for the red one, and it takes 25 seconds for any motion to be detectable. And this curve just shows the magnitude of the velocity normalized by the maximum it can reach. Because different samples, different conditions, if you don't normalize, this curve will look funny, perhaps. Any questions? So that's just something very straightforward to build up our knowledge about how. So the point I want to focus on when we say we dive a little deeper is this one. So this is, oh Lord, I just want to blow up this a little more. This is a case where we are aware, by this time, as you know, we are aware what two model says, where we're aware this non-quiescent motion means. It means sample breaks apart. And we are further aware, by this time we are definitely aware. In fact, this is a paper, I think by the time this paper was published, it was already, just to give you the sense of it, it's already 2009 for the melt. This is for the SBR melt. When we first did the build-in solution, that's the spring of 2006. It was absolutely perplexing to explain why there is non-quiescent motion, the Y part. So it just gives you the timeline, which I will eventually say a little more. By the time of summer 2006, we already know the physics. Meaning we already understood the physics driving the sample to break apart. So of course, by this time, of course, we know what we're looking at. We're looking at the failure from example of a melt. We're looking at TK. As I showed you, that's a kink showing the sample is breaking up. But notice this in Puyang's paper. He was patient enough to apply a rate such that the so-called Rouse-Weissenberg number will be smaller than 0.2. Okay, what does this mean? So I'm gently introducing two models to you, step by step. I know in lecture 19, we talked a great deal about it. That is the previous lecture. Remember, the two model says there's chain retraction. As soon as this affine deformation by the tube reaches time tau r. In other words, nothing can further stretch beyond tau r. That's the same thing as saying that, right? Because by the time tau r, it will start to retract. Okay? So if that's the case, you know what happens. You can ask, as you apply this shear, if you apply a shear such that by tau r, that's the maximum amount of chain deformation that can occur, right? By definition, meaning, I want you to be very used to this idea. Shear rate is just the amount of shear deformation that takes place per unit time. So whenever you multiply time, that is just the accumulated strand to that point. In the fine limit, of course, that's just accumulated molecular deformation that occurs to that moment. So up to tau r, that's maximum you can impose on the chain, because beyond that, the chain retracts, right? It cannot stretch further. If you choose this to be smaller than 1, do you have a lot of chain deformation? In other words, we choose this to be only 0.2. So the chain could hardly get stretched. And therefore, there's no way for you to anticipate any failure, because the chain didn't get deformed much. So we were interested in exploring the question of, under this weak shear condition, this is far from the convention of step shear. Remember, step shear is always done at as fast rate as possible limit. So we already start to modify the protocol about how to examine the rheological response. This is a very slow startup. And we truncated at only 1.3 H's to the right. And we stop at that point. And using very little shear, so that according to the tube model, the chains are hardly stretched. If it's hardly stretched, then it hardly can retract, meaning there's very little mechanism for retraction. In fact, if you try to quantitatively compare with the tube model, which we didn't, there won't be such a gigantic kink. Because remember that drop is due to the massive amount of chain stretching. And if there is a massive amount of stretching, then this kink will be very, very negligible. But we see a kink because it still breaks. So at least we were trying to probe the limit where the breaking can occur without requiring the system to be highly stretched. So this is just the details of how this weak shear produces the observable microscopic motion at different times. Initially, of course, not. So again, it has induction about 10 seconds or so. So I don't think this is the final word, although such experiments are usually not so easy to carry out. So I have no idea how soon it will be reproduced in the literature. But we did express our interpretation about what this means. Yeah, that again, this is not something the tube model can anticipate. This is basically what we're saying. So moving on. So I see this is the part that I always tend to try to save time by not writing them down. So this is all about the second part of chapter of chapter 12. And the second section basically is particle tracking observations of non-quiescent relaxation. So there were several parts to it. I just highlighted some parts from the last lecture and today. And for example, this particular slide is in section 2.2, chapter 12, section 2, and this 2, the book is written in such a way that we keep having 2s. So keep having numbers. So this section is about SBR, and then there are different features. So this is the fourth part of that SBR part. It means that there were several features that I went through. So here there will be 2.21, 2.22, 2.23. It's all in the book. That's why I can afford to be somewhat less formal. So in any case, the next one I'm eager to describe to you is described in section 3. This is of course, in my opinion, even more important part. It's not a little bit of it's toward the issue of why. So it's not just what happens and how it happens, but why it happens or why it doesn't happen. So this one is talking about. I know this concept I mentioned the last time, but I will say more about it. This is talking about elastic yielding that occurs homogeneously. So allow me to repeat what elastic yielding means. We, from the movie, saw that after step strand, things break apart internally, and that breaking apart is suggestive of structural failure. There's nothing more suitable than calling that failure yielding. It was elastically strand, and upon scission, that elastic strand structure is incapable of maintaining that elastic state and breaks apart. So that breaking apart is yield, and we know the driving force for that yield is this elastic state. In other words, being stranded sufficiently large enough. That's why we call this elastic. I mentioned that. I omitted the word. You can call it elastically driven yield or something. So basically, it's elastic yield. And we had a movie showing that sample falls apart. It means when you have non-quiescent relaxation, it means this elastic yielding took place in a localized manner. Okay, this means elastic yielding occurred really not uniformly everywhere across a microscopic sample, localized. So here on this page, I would like to discuss the condition where localized elastic yielding occurs, or how would you avoid localized elastic yielding, which means elastic yielding homogeneously. Right? So under what condition my movie will be boring? There will be no motion. In fact, if you are giving me a movie showing no motion, I will be clueless now, right? I will be clueless about what that kink means. In theory, you may still have a detectable kink, perhaps, but it will not have motion to give you the insight about what happens. So I just want to indicate the reverse. What's the reverse? The reverse is, even if the relaxation is quiescent, it does not mean elastic yielding did not occur. It could have still occurred, but occurred sufficiently homogeneously. I say this, I'm sure you will be, I'm giving you a hard time because I say this because I know what theory I'm talking about, which I haven't offered to you, about the origin of elastic yielding, which is related so-called force imbalance. But we won't reach that point yet. So let me just try to entertain the question of discussing, or to discuss the question of when do you reach, when can you have homogeneous elastic yielding? When that is possible. That's high, right? So when that is possible, I already oriented you about the fact that we're doing it treating this all like a startup deformation problem. So before I even jump onto the question of when homogeneous elastic yielding is possible, let me first orient ourselves with a simpler question. Yeah, there is a simpler question. The simpler question is this, that, hey, yes, when I move 2H to the left or to the right, after a while, if it's melt, I see sample break apart. Well, you will ask, what if I just move 1H to the right? What if I just move half a H to the right? So this figure further says, hypothetically, or practically as well, that there will be a threshold amplitude. Only beyond this point, I will see non-quiescent relaxation. Okay? So only beyond that point, which means before that point, in other words, for amplitude smaller than this gamma, E stands for elastic, BD stands for breakdown. So if I use smaller strand, it will not have produced non-monoticity. They have not produced the kink and the non-quiescent relaxation. So this was related to what I asked last time about when the motion, after step strand, you see motion. When does the motion cease? And the idea was that if you have your sample here, your sample all of a sudden start to break. Okay? Sorry, gosh. Your sample start to break. Oh, Lord. Your sample start to break. You start to break, which means it will try to snap back like that, right? And I was asking last time how much it has to snap back before it heals. Okay? So suppose it heals by the time it snaps back to here. And then I can have a sense of how much strand is remaining. I still have that much remaining. And that number, if I give an X, call it X1, call this H1, that number is likely below this threshold number that I identified here. Okay? So actually it is not, let me just, microphone, why this says no microphone? Okay, we should have it. So it is not, we're not clueless as to when they start to heal. Because we know the threshold beyond which the sample can suffer failure. So by the time it returns enough, it should start to heal. So that's what I'm proposing for you. So it will heal. Now let's go to the story of the condition when the deformation, when the relaxation will be quiescent. So I don't think it's too hard for me to suggest, for you to understand my suggestion that the failure, based on our experience with wall slip, that the failure is a result of internal slip. In other words, internal disentanglement. In other words, some type of disentanglement that occurred internally. When I say internally, I mean this. I should always copy this image here. When I say internally, I mean this picture, right? In other words, this is the example at the surface, but let's remember I had super glue, so the surface somehow magically I was able to destroy the premature failure from the surface. Now it could only occur in the bulk. And in the bulk, let's pretend that it's also possible for one layer, which is red, start to disengage with the other layers, as depicted in B, so-called. So let's say that you have one layer that's disentangling like that, okay? Let's just examine the consequence of that. Well, we are familiar with the idea when a layer of disentanglement occurs, it produces a slip velocity, Vs. Let's call it internal slip, Is, just to be consistent with my book. And if they slipped with a slip velocity Is, it could produce this crack over a time. Let's say this disentanglement could last a time of TIS. Then this crack will have a size of XIX, as written here. Okay? So this crack is a sizable crack if, and only if, this ratio is not much smaller than 1, right? In other words, if this crack is negligible compared to the displacement that I imposed on the sample, then that crack, let's say if the crack is only within the thickness of that blue line, then of course the system doesn't notice that one layer has disentangled. What does that mean? That the other layer will start to disentangle because the condition for disentanglement hasn't changed for other layers. So it's a very beautiful argument that in the limit of this, you would have only quiescent relaxation, or if you still like to suggest that there is elastic yielding, that elastic yielding will be homogeneous. So only God knows why you could have this localized elastic yielding. When I say God knows, meaning it's some kind of horse race. One layer start to fail first, and they communicate. It says, oh, I'm failing, so you guys can take advantage of me, and other layers do not fail. Then that's what I have here. Right? So we are considering the condition of this ratio. And this ratio is very easy to do because all I need to do is that, right? And then I haven't done anything yet. So I'm going to, I know I'm trying to save some space. So, of course, this side you have to divide by x2. So basically, I'm trying to evaluate this ratio. And this ratio is nothing but, you see the bottom is what? It's gamma. So I'm just multiplying something. And at the top, I'm going to further evaluate the I'm going to further evaluate what slip means. Slip, according to what we learned from wall slip, is stress divided by beta. Slip velocity, right? Remember, it's by now I think you guys still remember it. And then you can write down something further. This stress is what? It's G times gamma, right? It's Newton's, it's Hawking's law, because that's the step strand you did. So all of a sudden, I have G on the top, gamma there, beta downstairs. Okay? I'm almost there. What's left? What's left was this TIS, right? So I'm good, right? It's coming from here. Travis, it's coming from identifying this. Right, to recover, to get it a gamma. So, yeah, so don't worry about it. So this T, I'm going to do another trick. Multiply a tau, divide a tau. Okay? So then, you know G times tau is nothing but eta. And then you know eta divided by beta is B. So all of a sudden you have basically B over H TIS over tau. And that's the equation 12. That's the equation 12.8 that I derived for you. And you can see the condition for this to be much smaller than 1 is readily satisfied if B over H is much smaller than 1. Why? Because this factor cannot be larger than 1. Yeah, this is the time the disentanglement could last before healing occurs. That's why I keep talking about re-entanglement or healing. Of course, I haven't said too much. But that time cannot last more than tau, because by the time of tau, all the chains can even diffuse and heal by itself. So it's trivial to argue that the second factor is smaller than 1. So here I go. I just, without a sophisticated theory, I just argued firmly the condition for you not to see any motion after step shear is for you to have no ability to produce observable internal slip, which is characterized by B over H. And we're so familiar with that parameter because that was used to characterize whether wall slip effect is observable or not. So it's the same thing. So this intimate connection is just astounding. What we learned, the concept from wall slip, just directly applies when you envision in the bulk a similar effect. Hypothetically, let's say that can occur, then everything goes. So I just reached an important point. So I made an argument about the condition when you would be disappointed because your movie will show no motion. That's the limit when B over H is much smaller than 1. Of course, knowing this discussion, in order for you to see motion, you better pick up a B that's quite large compared to H. So you have the chance for this crack to be measurable, to be appreciable. And what I indicated here, of course, is appreciable. Meaning, right? It's appreciable. It's a fraction of the total X. It's not this limit. Right? so that I'm arguing other layers had a chance to snap back, right, from the from the blue point to the black line. Yeah. So with that, we can go to ask one of the last questions, which is, if you are in this limit, b smaller than h, then obviously you have no movies that you can count on to learn about the so-called elastic yielding, which is a shear scission-induced structural failure. Shear scission, meaning when you stop, structural failure can take place. But if there's no movie, then how can you speak about it? And that's the next paper that Yang did. So I'm going to be slow going through that with you. So suppose you have a condition where, so actually there was one stone, two bird in this study. He picked up a sample where B over H will be small. So don't count on seeing motion. Bad luck, you won't see it. Secondly, when I see the two birds, the second bird is, he also considered a condition where the tube model will not anticipate any structural failure because the chance was only deformed 10%, according to this parameter of the Rawls-Weissenberg number being 0.1 here. Yeah. So one stone, two bird. We are trying to figure out, upon shear scission, with such a slow shear, where chance deformed very little, can the structure actually undergo failure induced by shear scission without the aid of a particle tracking velocimetrical measurement, because there will be no motion. So that was the aim. And since we have a pretty strong belief that the stress overshoot we spoke about so many times is an interesting point. It's a point speaking about structural failure, right? It's a yield point. So can we use the response? Can we use this feature to learn something about the structure? In the following sense, if my sample is intact as a fresh sample for a given shear rate, I will always reproducibly reach this maximum, right? I reload the sample, it will be the same rate every time. So if that's the case, you can already learn something very interesting. Suppose I only shear my sample 10%. Well, actually, it was 30%. 30% turns out is quite mild. It's not going to destroy the entanglement network. So 1/3 of H to the right. It's very gentle. Therefore, when your shear scission occurs, the structure is always intact all the way along. How do you know that? We, of course, don't have a movie to show because the sample will not break up for 30% of deformation. So he did it by, during different time of relaxation, he imposed a very fast startup shear to watch what would be the overshoot peak you build. And he found it's all the same. Of course it's the same, because the structure is the same here as the same here is the same as before you started your experiment. So it's confirming that that this could be an indication of the structure. And then he started to shear 200%. And then stop. This is all discrete experiment. He stopped. After a few seconds, he applied the next shear rate and got this peak. He redo this experiment. Next time he stopped and waited for this much time, he got another peak. Overshoot. And you saw a valley. In other words, there is a minimum at the green, okay, of the peak. And that's the same value that he reported. in the upper figure. So the upper figure, of course, shows you how much stress build up, how much stress relaxes. He summarizes each of the peak and plotting those peak values here. That's how he did. And amazingly, there's a minimum. In other words, when you shear session, when shear is terminated, your structure is more intact here than here. In other words, your structure was more intact when you first stopped, and subsequently the structure was damaged. And then if you give more time, the structure heals again, so it went back toward the intact structure. This is our motivation, our perception. Just for fairness, this result was supposed to challenge the tube model because in this limit you are not supposed to have structural failure. It was sufficiently disturbing that the people who work with tube model actually went ahead and did tube model calculation. They can also claim to have such a different interpretation. So I'm going to leave that to you guys. I'm not going to. I'm not going to hide that information that the tube model can also produce such a minimum. That they actually published this subsequently to this paper. So this, of course, speaks about the challenges of making macroscopic observations. You know, this is nothing but stress, so it's a macroscopic test. And from that to say something molecular, that's challenging, always, right? And we don't have a clue necessarily. So it is a matter of more carefully examine the different pictures in other conditions, which one give you more consistent results. So in any case, I'm going to, since we are not at the point of discussing the theory yet, I'm going to just leave it as such and treat this as just a description of the experimental efforts about how to learn about the structure. In our case, is a structural failure here. And basically move on. So, any questions? I can see that that we reach a point where we can take a break and move on to next section after this. Okay, so I will just stop here.